a comparison between magnetic force and electric force into different fields. At first, let us consider a magnetic field. In this field, just you consider 4 protons. Say these are 4 protons. This proton moving with velocity v perpendicular to the direction of magnetic field. This proton moving with velocity v with some angle with the direction of magnetic field. Third proton moving with velocity v in the same direction of the magnetic field, and this proton is at rest. Now, what will be the force on each of these protons or positive charges? For this, we know that force experienced by a charged particle when enters in a magnetic field is given by q times velocity vector cross product magnetic field vector. That means if a charged particle enters in a magnetic field with velocity v, then the force is given by, this is your magnetic force. Magnetic force is given by q times v cross b. Now you see, this is equals to q v b sine of theta. This is cross product of two vectors, and we know the cross product of two vectors, that is v magnitude and sine of theta. This theta means angle between these two vectors, Now come here. The first case, in this case, angle between velocity and magnetic field is how much? 90 degree. So in that case, sine 90 will be 1. So case 1, in the first case, theta is your 90 degree. Then magnetic force, that will be maximum, which is your QVB. I am writing only the magnitude. So in that case, magnetic force is maximum, because sine 90 degree is 1, that is the maximum value of sine theta. In the second case, say it makes some angle theta. If I say some angle theta with the magnetic field, then it will be simply, the magnitude will be, some magnitude it will have. What's the magnitude? Say QVB sine of theta. Third case, let us consider the third charge or proton. See, this is, in this case, direction of velocity and magnetic field in the same direction. So it means theta equals to 0. So in that case, sine theta 0 means that will be, force will be 0. Magnetic force will be 0 on this charge. As this charge is at rest, that means speed is 0. So in that case also, F is equals to 0. This is the minimum force experienced by a charged particle. So magnetic force on a charged particle is 0 under two conditions. One is your charge is at rest, because magnetic force is not your effective in case of a charge at rest. Magnetic field never apply force on a charge at rest. Second, if the charged particle moves in the same direction of magnetic field, in that case also the force, magnetic force will be 0 on the charge. Now, the most important point, direction of the force. Whatever force will be applied by the magnetic field, what's the direction of the force? Direction of the force you can obtain from here by definition of cross product. For this, let me show it here. Say this is a vector A and this is another vector B. These two vectors lying on the plane of the board, and at some angle theta. Then A cross B is a vector that's perpendicular to both the vectors A and B. This is the definition of cross product. See, now if I take A cross B, you just imagine you have a screwdriver and you are rotating the screwdriver from A to B. If you rotate a screwdriver from A to B, that means the screw will be loose and it will come outwards. So if I say A cross B, then it will be left side. You have to turn to the left side. Then whatever screw will be here, that will come out. It means it will be perpendicular but outward. In this case, if I take B cross A, so B cross A, in this case you will rotate the screwdriver to the right side, then it will be tight, righty tight. So as it is tight, that means it will be inwards. It will be perpendicular to the board, but it will inwards. Next come here, say V cross B. Here you see, in this case also, say V cross B. Here, this is the direction of your V. In this case, let us calculate the direction of V cross B. This is your V and this is your magnetic field. This is your direction of magnetic field. So if I say V cross B, so V cross B for this charged particle, the force will be perpendicular to this, and V cross B, that means you have to rotate it to the left, rotate it to the left side this way, and then it will be outward. The direction will be outward, but in either cases it will be perpendicular to both V and B. This is your velocity vector, this is your magnetic field, and this angle is your theta. So what will be the direction? It's perpendicular to V cross B will be perpendicular to the surface of the board and outward, because you are taking V cross B and you are rotating like this way, so it will be outward. That also you can find out. Next you see, you can apply the same concept here also. Say this is your B, this is your B, and this particle moving in this direction. In this case, V cross B, here it is V, and this angle is your theta, that means 90 degree in this case. What will be the direction of the force experienced by this charge? In this case, V cross B, you will rotate it like this way. Then it will be the screwdriver, that means tight, and it will enter the board. So in this case also, it will be perpendicular to both V and B, but inwards. So for this, direction of the force will be cross, inward. In this case, direction of the force will be outward, because V cross B you are rotating like this way. So it will be here dot for this case. This charged particle will experience the force, that is your it is your dot. That means because it is your outward. V cross B is your outward. When it is outward, we represent it by dot, perpendicular to the board like this. In this case, it is your cross. And in the space actually, if I clarify this, in this case, this is your B vector and this is your velocity vector. So in this case, you are calculating V cross B. Here it is the charged particle, V cross B. So V cross B, your direction will be towards you. It is like this. The charged particle will experience force in this direction. In this case, it is like this. V cross B you are calculating, that is your tight V cross B. So suppose this is your charged particle, here it is the charged particle, V cross B perpendicular, and the charged particle will experience force in this direction. Now, most important point we are going to discuss, whenever a charged particle enters in a magnetic field, can the speed of charged particle be changed? Whatever be the magnetic field, whether it is uniform magnetic field, non-uniform magnetic field, whatever is it. Question is, if a charged particle enters in a magnetic field, can the speed be changed? say here it is a magnetic field. Let me consider uniform magnetic field only this. If a charged particle enters in the magnetic field, say I will suppose with some velocity, charged particle, some velocity v, with some velocity v, it enters in a magnetic field. Now you see, whatever force will be experienced by the charged particle, that force direction is what? Perpendicular to both the vectors. It is like this. Say this is the velocity vector and this is your suppose magnetic field vector, and V cross B, that is the force experienced by some charged particle, is the force is perpendicular to both V and B. As the force is perpendicular to V and B, so along this velocity, the angle is what? The angle is your 90 degree. And you know this is a vector. In this direction, say if it makes angle theta, so it is your any vector, you can take r vector. So in this direction component is what? R cos theta. R cos theta. And in this case, this is your magnetic force. That is force experienced by the charged particle which charge is moving with some velocity v on the plane of the board. This angle is 90 degree. Then in this direction, what's the component? Cos of 90. That is your component of the force. F cos 90. F cos 90 is what? 0. I mean to say that in this velocity direction, there will be no force. Simple concept. As the force experienced by the charge is perpendicular to both velocity vector and your magnetic field vector. So in the direction of velocity, there is no component of force experienced by the charge. So that's why whatever be the magnetic field can never change the speed of the charged particle. In case of electric field, it is simple. So electric field force expressed some charged particle is here and here. Here also you can consider 4 charged particle. So this is moving with velocity this, and this is in this direction, making some angle with the electric field, say velocity v, and this is in this direction. This is at rest. So electric force is given by what way? Electric force is simply Q times electric field intensity. So in this case, see, Q times electric field intensity. So this charged particle or this proton will experience a force. This proton will also experience a force, because as you are saying F electric force is equals to Q times E. Q times E. So if you want to see the magnitude, that is F equals to only Q times E electric field intensity. There is no velocity or any angle is not there. So in all these cases, the charged particle will experience a force, whether it is in motion or whether it is in at rest, and with what angle it's moving with the electric force does not matter. Equal amount of force all the charged particle will experience. This is the case of electric field.